Okay, so what we have seen before the break is that if you know the current, you can calculate the velocity, but the velocity of the electrons also depends on the n, which is the number of electrons per volume. So you can see that let me write this a little bit. So for example, if you fix I and you want to calculate V, so you're gonna have VD equal to I divided by A, N, and then E, right? So just inverting this equation, you're gonna have something like this, right? So if you have a material which is which contains a lot of electrons, sounds like metal, right? So you have really large number of N, right? So you're gonna have lower velocity, right? Because you have more number of electrons, and each electron doesn't have to be moved so fast, right? So something like that. So you can think about this, and then you see that it kind of, you know, makes sense, hopefully. Um, but the thing is that in reality, we are not really dealing with these parameter directly. We're gonna talk about a different property of the material, which kind of related to, like the oh, what I'm doing. So related to the number of electrons, the density of electrons, kind of like in an indirect way. But in any case, this formula is something that we are not going to use that often, but it's kind of good to know, right? In the case that you really want to know the drift velocity or something like that. But most of the time, we're going to be using the one that I'm going to talk about now, which is um, something like this. So what we do is we take, again, um, a piece of metal rod, looks like this, and let's say the cross section area is A, the length of this material is L, and then what we do is we connect this thing to a battery. Okay, like this. And again, the battery will force the movement of the charge. In this case, it's electrons, right? So this is positive terminal, this is negative terminal. The electron will get attracted to the positive side because by doing so, it lowers its potential energy. So electron will flow this way. Okay, and because electron is negative charge, when we draw the movement of the current, it's gonna be opposite direction as the electron, like this. And this is nothing more than just a convention. Like it's just the fact that we label electrons to have negative charge, so that current which we think about is as like positive current, it's flowing in the opposite direction. Right? So I, which is called a conventional current, flows in an opposite direction as the electron. Okay, so when we say current is flowing from left to right, it means in reality that electron is flowing from right to left. Right? So it's just the opposite direction. So again, all of this is because someone back in the days think that okay, let's call electron to have negative charge. So all of this is following from that. So if you live in the parallel universe and then someone say okay, let's just call electron to be positive charge, then I and electron movement will point in the same direction, which is maybe a little bit more convenient. But in the end, it doesn't matter. It doesn't change physics at all. Okay, so from now on, we are not going to talk about the movement of the electrons. We're going to talk about just the conventional current because that's just the way I chose it. Okay, so let's not talk about that. Or maybe I just keep it. But remember that we just talk about the conventional current. Okay, so a battery has a potential difference of delta V. Again, we saw this earlier when we talk about capacitor. So by connecting this, we form what we call an electrical circuit. Okay, and we don't want to have to draw this kind of thing all the time, meaning that this 3D drawing. So we're going to draw this in what we call the circuit diagram. So it's kind of like a diagram that represents what's going on in the real circuit. Okay, and this piece of wire, we're gonna call this one resistor, because is anything which let electron flow will have some resistance to the flow of the electrons. So we're gonna call it a resistor, and the battery will have the diagram that looks like this: one longer line and the other one smaller line. So the longer line is always positive, and smaller line will be negative. Right. So this diagram can be written in this way, and the resistor, which is the piece of metal, will have something like this. So it looks like a spring, but it's not. Okay, this is called R. This is called battery V, or delta V. And then there will be some current flowing in the circuit like this. Okay, so this is written in this way. It's talking about the same thing. Okay, and then we found from the experiment is that the amount of current flowing in the circuit for a given type of material or a given shape of the material depends on V. So I depends on V. Actually, let me start with this. So I actually is directly proportional to V, or delta V. This is found experimentally. Okay, so that means if you plot the graph for a certain piece of metal, which we call resistor, so a piece of resistor, you're gonna have a straight line when you plot I and delta V like this. So it's gonna be a straight line. If you change the type of material, for example, you change from like aluminum to copper, then you're gonna have also a straight line, but it's gonna be a straight line with different slope, something like this. Or if you take the same material but you cut it in half, or you double the length, or you change the area, you also will have a straight line, but you're gonna have straight line of different slope. But in any case, when you plot I and V, you always have a straight line. Okay, so because of this, we're gonna define the proportional constant I to be what we call 1 over R times delta V. Okay, and the reason why we define it like this, because we want to call R to be a resistance. And like the name suggests, if you have large resistance for a given potential difference delta V, you're gonna have very low current. If you have very small resistance for a given potential V, which is set by the battery, you're gonna have huge current because you divide by small number, right? So this is how we're gonna call the proportional constant of this equation, right? So reversing this in a more familiar form, you're gonna have delta V, or simply V, equal to I times R, which most of you know that this is called the Ohm's law. Okay, so writing this again here, V, I'm gonna drop delta V because let be kind of like, just remind yourself that when we talk about V, it's the potential difference between the battery connecting to the resistor. So V is equal to IR. This is the potential difference. Or casually, sometimes we call this a voltage difference. And the unit is volt. Right, so that's why we call it the voltage. It's the term voltage is not, I think, strictly speaking, correct in the physics sense, but we just use it kind of casually because the unit is volt. But it's actually talking about the potential difference, which is related to the potential energy difference. I is the current. I is the current. And the unit is ampere. Okay, that's what we talked about earlier. It measures how much charge it flows across the material, which in this case we call it a resistor, in one, like duration of time. Okay, so it's measured in ampere A. And then the last thing is resistance. R resistance is the proportional constant between V and I. And the unit of this is called ohm. Okay, Ohm is another physicist that we name the unit after to honor him. And sometimes Ohm is kind of long, so we use a Greek letter omega to write this instead. Okay, so you are used to small omega in like circular motion and in wave. This is capital letter of omega, so it looks like this. Right? So some of you might have seen, a brand of watch called Omega. It's the same letter, which is a Greek letter that we use instead of writing OHM ohm. Okay, so it's like this. So it turns out that the resistance of the material depends on not just the type of the material, it also depends on the shape of the material. So it turns out that the resistance of the material depends on the length. The longer the material, the more resistance. It's kind of like, a pipe for water to flow. If you have longer pipe, then it's harder for water to flow through the pipe because it has to go through larger distance. It's the same for electrons here. So if you have the same material, everything is the same, but one is longer than the other one, then the longer one will have larger resistance. It also depends on the cross-section area. The larger the area, the lower the resistance. Okay, so it's like having a larger pipe, you're gonna have water flow through the pipe a lot easier compared to a small cross-section pipe. And last thing, we have the thing which capture the type of material. What I mean is that whether it's copper or gold or silver or like aluminum, how does that enter? It enters here. This is called the resistivity. This depends on the material. And this letter is, well, it looks like P, but it's actually Rho, another Greek letter. So it's P with kind of like curly tail or something like that. Okay. So this is Rho. And different material will have different resistivity, different rho. So I will list a few. There's actually a table, but actually the table is too much. So I'll just list a few things. So the best kind of material that we can use as a conductor. So a better conductor is the one with less resistivity, right? So resistivity is an ability to resist the flow of current. So if you want a better conductor, you want to have lower resistivity. So silver is probably the best. It has rho equal to 1.62 times 10 to the minus 8. The unit is rho meter. Okay, and you can see that why this unit makes sense, because rho times L divided by A has to give R, which is resistance. And most commonly used material is copper. Copper is a little bit worse than silver, but it's a lot cheaper. So that's why we use them. So you can buy, like silver wire. So some of you might be really into, like high fidelity audio stuff. And you can buy cable which made from silver. It's a lot more expensive, but you get, about 3 or 4% increase in the conductivity. So whether it's worth it or not, well, it's up to you, but I don't think so. Um, Another thing which is interesting is gold. I don't need to tell you how expensive gold is, but some connector like audio jack is plated with gold, and it's plated with gold not because it increased the conductivity, because you can see that the resistivity is actually less than copper, so actually worse in terms of a conductor compared to copper, which is, I don't know, 10 times or 20 times cheaper. So why do we plate gold at the connector? Well, the thing is, silver and copper, they can oxidize. So oxidation, some of you might learn this in chemistry, is the chemical reaction between the material, especially at the surface, and oxygen in air. So it can form what we call oxide, like silver oxide, copper oxide. And those oxides are usually insulator, right? So think about when you need to connect your headphone jack to the computer, you need to plug it in, right? So a connector, let's say it made from copper, right? And when it connects to some kind of, like a spring connector like this. So you make an electrical contact there. So the audio signal can flow through this, right? But if you're not careful, the surface of this material can form what we call the oxide layer around the surface. So this is oxide layer. An oxide layer is usually, again, an insulator. So it's gonna make electrical contact a lot worse if you don't do anything to it. But for some reason, gold itself doesn't form oxide in air. So what we do is we coat or plate gold around the connector to prevent this problem. Okay, so if you put gold here, it's gonna remove the possibility of forming oxide layer at the surface of this connector. So you're gonna have like good electrical connector all the time, right? So that's why we do gold plating at the connector. Again, not because it increased the conductivity, it actually make it worse, but it's gonna make sure that you don't have the oxide layer. The oxide layer, does it affect the resistivity? Well, the oxide layer itself has a really high resistivity, right? So it's kind of like when the oxide layer form at the surface of copper, it makes the surface of the copper becomes an insulator. So that's not good for like making a connector, right? Like your audio jack. Somehow the audio jack can be an insulator, and then you're gonna have bad connection, right? So the gold layer is to prevent the oxide layer from forming in the first place. Okay, so it's not gonna do anything to the material, but it's gonna form like kind of like protective layer around the material, which is not what we want. So that's the issue here. Okay, so well, gold is um, expensive, of course. So for some case, you can also get the same thing by not plating gold, but plating some other material which also doesn't form oxide layer, like nickel. So sometimes you have like nickel plated connector, and it's doing the same thing here. All right, so that's the thing. Um, at the beginning of this discussion, well, not this lecture, but a few lecture back, we also talk about um, insulator, conductor, and also semiconductor. Okay, so now actually we can kind of talk about that classification with um, with like some quantity, some number that we can use. So to see if the material is conductor, semiconductor, or an insulator, you can just look at this value of rho. Okay, so metal which is conductor has rho around this, which is really small. And if we talk about a semiconductor like silicon has rho of about 2.5 times 10 to the 3 rho meter. So you can see that it's about 1 million times larger in terms of um, you know resistivity compared to metal. So that's why we call silicon a semiconductor. So that means insulator is even higher. For example, glass, which is an insulator, has rho of about 10 to the 10 rho meter. So you can see there's like a huge range of resistivity for different material, and some is good for like insulator, like rubber, glass, ceramic, all that stuff insulator. Um, Silicon, again, I mentioned that is a very important element because the fact that it's a semiconductor, you can easily control the resistivity by mixing it with some other material. So you have a lot of control over what's the value of rho you want. And then you have metal, which is something like this. Okay, so these are some value that you can kind of like look at. And if you want to know some other material, you can just Google. For example, if you want to know the resistivity for aluminum, you just type aluminum resistivity and then you get the number out. Okay, so next thing, let's do a simple application of this V equal to IR, which is Ohm's law. And the simplest is just one battery and one resistor. So, example. So let's say we have one resistor that looks like this. By the way, resistor is written this way. That's what we use um, in the US. In Europe, resistor is drawn like this. Okay, so no matter, it doesn't matter which one you use, is what you're used to. Well, I'm used to this, so I'm gonna draw it that way. But keep in mind that when you see some diagram that use resistor like this, it also means the same thing. Okay, so let's just note that. So we have a resistor, and we call it R. And let's say this R is 100 ohms. Okay, a very typical value of resistor. And we connect a battery to form a closed circuit like this. Okay. So a circuit needs to be closed in a sense that it has to be able to complete the loop like this. So we're going to talk more about the loop probably next time, because I don't think we have time to cover Kirchhoff's rule here. Okay, and V, let's say V equal to 12 volt. How do we calculate the current? So given this, like how much current you're going to have in the circuit. So I equal to V over R. So it's simply 12 volt divided by 100 ohms. And you're going to get 0.12 amps or 120 milliamps. Okay, so you're going to be using amps and milliamps quite a lot. So just, get, so familiarize yourself with, going from amp to milliamps, because we're going to do that quite often. All right. The other thing which I'm going to quote the formula again without proving is when you have current flowing through the resistor will become hotter. That's true for any resistor. And we use this for, like electrical boiler. And this is called resistive heating. Essentially anything when you pass current through, it's gonna heat up. And that's just because when electrons moving through stuff, it has some kind of friction, right? So you lose some energy, and that energy turns into heat, right? So the power loss into heat of resistor R is given by P equal to V times I. So V here is the voltage across the resistor, which is the same as the battery, because there's only one here. So in this case, it's just 12 volt times the current flowing through the resistor, which is 0.12 amps. And you get 1.44 watts. Right. So watts is the unit of power, remember this? So it's joules per second. Okay, so this resistor will dissipate heat because of this power loss, about 1.44 watts. Okay, so every second you're gonna have about 1.44 joules loss in terms of heat for this resistor. Okay, so this is a very simple circuit that we can have. A more complicated circuit is when you have more than one resistor in the problem. So let's do that. So we're gonna have, let's say, two resistor like this. So one here, we call it R1. And let's have R1 equal to 50 ohms. And then we're gonna have R2 equal to 70 ohms. And we're gonna connect this again to a 12 volt battery like this. And the question that we want to answer is we want to calculate the current flow in the circuit. Okay. Well, actually, I think this is probably a good time to talk about Kirchhoff rule. So there are two things that I want to mention here. Is this. So we're gonna call the voltage or potential difference across R1 like this. And we want to call V2, which is potential or voltage across R2 like this. So V1 is potential, electric potential difference across R1, right? So essentially it's a number that tells us how much higher the potential at this point compared to this point on the circuit, which is the two legs of the resistor. Okay, and in the experiment you can just take a voltmeter and then stick the voltmeter across the resistor like this, and you can read the number, right? If it say 1 volt, then the voltage or the potential difference across the resistor R1 is 1 volt. And again, sometimes this is called the voltage difference. So I would say these two terms kind of interchangeably, but you should know that they mean the same thing. And same for V2. So V2 is the voltage difference. Difference across R2. Okay, so that's V1 and V2. And what does Ohm's law tells us? Ohm's law tells us that V1 is actually I times R1. I is the current flowing through R1. So V1 is just I times R1. So if we know the current, which we don't now, but we're going to know later, if we know the current, we can actually calculate V1 by simply multiplying 50 ohms to I, and that's going to be V1. And the same for V2. V2 is going to be the current flowing through R2 times 70 ohms, which is R2. Right, so we have this. So this is usually how we use the Ohm's law, right, is to find out like what is the voltage across each resistor once we know the current flowing through each one. Right, so V1 is I times R1, V2 is I times R2, like this. Okay, so I'm gonna probably introduce the Kirchhoff rule here because I mean it's still enough time, but we're gonna finish it today. We're gonna continue it next week. There are two rules in the Kirchhoff rule, and we're gonna call this rule that I'm gonna talk to you about the second rule. Okay, so sorry about that. The first rule we're gonna talk about it next time because the first rule involve like junction we don't have here. So Kirchhoff rule. Kirchhoff rule is rules that we can use to calculate the current in the circuit. So Kirchhoff rule. Rule number 2. Okay. Gonna talk about rule number 1 next time. So rule number 2 is this. So take a point. Take any point in the circuit. And call this one a starting point. And then walk around the circuit and back to the starting point. Okay, so by doing so, we say you have complete the loop, complete the loop. Okay, total change in voltage V along the loop must be equal to 0. Okay, so how do we use this? So what we mean is this: take any point in the circuit as a starting point. So let's take this point here as the starting point in pink. And then we walk around the circuit and back to the starting point. So we're going to walk this direction and then back here. So that's going to be my loop. In this circuit, there's only one loop to choose. So that's no brainer. You just have to choose it like this. Okay? But in other circuit, you might have different possible loops to go. It doesn't matter, you just need to complete the loop. So you start at some point, you walk around, and then you just make sure that you come back to the starting point, meaning that you have completed the loop. Okay, so the total change in voltage V along the loop is 0. So what do we mean by that? Well, the change in the voltage happens when you go across two things, either the resistor or the battery. Okay, so we have kind of like a convention like this. So if you go across R in the same direction of the current, then the change in the voltage that we accumulate is minus IR. If you go in the opposite direction of I, then it's positive IR. So that's one thing. The other thing is for battery, if you go across battery, from minus to plus, then delta V is just the voltage across the battery. Okay, so this is the thing. So let's go back here. So we start here. We go across the first resistor and we walk it in the same direction as I. Right, the current is flowing this way and we walk in the same direction as the current. So the change in the voltage of the first resistor is negative according to the rule that we wrote down there. So it's going to be minus V1. So actually I can just write minus IR1 for the first resistor. Right, again minus sign is because we go across the resistor in the same direction as the current. And then we are done with R1. Then we go across R2, which is the same direction as the current. So that's going to be minus R2. Right, so now we are here. And we just keep walking. The third element that we encounter is the battery. And we go across battery from minus to plus side of the battery. So that's going to be plus V battery. And then we are back to the starting point. So when you are back to the starting point, you can set the whole thing equal to 0, like that. Okay? So if you go across any resistor and you go in the opposite direction of the current, then you just flip the sign here. And if you go from positive to negative of the battery, you also put a minus sign here. So you can see that if you start from here, but you go in the opposite direction, like this, so instead of clockwise, you go counterclockwise, you're gonna get minus V battery plus IR2 plus IR1 equal to 0, which is the same equation. Okay, so it doesn't matter which way you walk, as long as you stick to this rule, then the answer is going to be the same. All right, so from this, what you get here, sorry, probably just write it this way. So what you get here is IR1 minus IR1 minus IR2 plus V battery equal to 0. So the current is just V battery divided by R1 plus R2. And that's going to be 12 volt divided by 50 ohms plus 70 ohms. And that's going to be 0.1 ampere. Right. So you can see that using Kirchhoff rule, then we can calculate the current in this way. Okay, so sorry that I'm a little bit rushed through this. We're gonna talk about this more next time, but just again, familiarize yourself with this rule, because this is what we're gonna use again and again. Okay, but I think we are running out of time today, so I will continue the discussion. Especially some of you might kind of curious, like, okay, this is the second rule of Kirchhoff rule, so what's the first one? So we're gonna talk to you about that next Wednesday. Okay, so Monday is a holiday, so we don't have class. It's a long weekend, so take a good break if you can, or at least try to take a good break. And I'll see you next week then. Okay, so thanks guys for today, and take care. I will see you next week.